Hello, AP Stats. This is Mr. Kim, and welcome back. This is the part 2 of the Chapter 3 AP Review Packet video. And in this video, you will see the answers to all of the free response questions. And let's get started, first of all. So 23, I'm given the list of the numbers. Usually the first one, they label it as flow, whatever they give you as a context. In this case, would be flow rate will be X, the explanatory. Amount of eroded soil will be Y, your response. So find the equation of the LSR. So to do that, I'm going to go to my calculator here, and I will have to put all of these numbers into my list. So I'm just going to use list 3 and 4 because I have the two numbers previously saved from the previous questions. So 0.31, 0.85, 1.26, 2.47, and then 3.75. And then the list 4 will be 0.82, 1.95, 2.18, 3.01, and 6.07. So I'm going to go to Stat, Calc, and then I'm going to go to linear regression with list 3 and list 4. I'm going to store my regression equation into various y various function 1, press calculate, and there are all those informations that I need. So the equation here, it seems to me, if I were to zoom into this, y hat would be 1.389x plus 0.4057. You can see that I'm using maybe 4 significant digits or maybe rounded up to the nearest thousandth or 10,000th place. That should be good enough. And allow you to predict the line and then interpret the slope, the y-intercept in context. So we're going to have to do some writing. So the slope means for every increase in the flow rate, liters per second. So every one increase, if you want to say that, for every 1 unit of increase, comma, there will be about 1.389 kilograms increase in the weight of eroded soil. That's what I would say. So for every 1 unit increase in the x, it's going to increase the y about that much. That's what the slope represents. So for the y-intercept, which is 0.4057, so the slope is this one and the y-intercept. So for the y-intercept, what we're going to say is at flow rate of 0 liters per second, we can expect the eroded soil to have about 0.4057 kilograms in weight. Initial starting weight of eroded soil. That's what it is. So specifically say that the x is equal to 0 and say the amount, whatever they have specified, that's the y-intercept for this equation. Part C, give the value of the correlation coefficient, interpret that in the context. The correlation coefficient here, if I were to recall the calculator, it seems to me that the R value is 0.966 and the R squared is 0.935. I'm just going to write that down for part D as well. So interpreting this means we have a very strong association between the flow rate, I think the flow rate of the so the flow rate of water, flow rate of water and the amount of eroded soil. All right, so that should take care of part C right there. And let's take a look at D. 93.5% of the variation in the response variable here, which is the, what was that? It's the, amount of eroded soil, can be explained by linear relationship, or you can say LSRL. Sorry, that's a terrible R for this one. So I'm going to go back to this. So that's by the linear relationship or using the LSRL with the explanatory variable in here, which is the flow rate in liters per second. Yes. All right, so calculate and interpret the residual for the flow rate of 3.75 liters per second. So what that means is I'm going to plug in 3.75 for x into the equation that's specified for me from part A. So we're going to be doing this. All right, so for 3.75 liters, we have the actual value of 6.07. So I'm going to write down that actual is 6.07 for this one. And when I go to my calculator, okay, and then I think I can just use this right here, vars y vars function 1, and open up parentheses. I'm just going to type in 3.75. What that means is I'm going to type this into the y1, into the function of y1, and you're going to get 5.614 as the weight in kilograms. So that's the predicted. So you do 6.07 minus 5.614, which should give you 0. Oh, my apologies. No, I'm sorry, that's correct. So 0.9, what is that, 86 as the residual. So it has to be in the units of the response variable, which is the amounts in kilograms right there. Oh, I'm sorry. I think I made a mistake here. that should be 1 point something. So 1 point. No, actually. All right. So I don't know why. Oh, let's see. This was my fault. So let me just go here. All right. So that should be 0. What is that? 3. And then that should 0.45. 0.456 kilograms. Okay. Whew, that took a little while, but my apologies there. And I think that should do the trick. So around that value, so you can see how I rounded up to the nearest like thousandth place. That should be okay. And just to reiterate on that, yeah, 0.45 is what they said in the answer key. Okay, 24. We have give the equation of LSRL. Guys, not gonna say that again. Y hat 2.1690x plus 28.52. Comment of the appropriateness of the linear model. Linear model is a good fit for the data since the residuals are scattered and no apparent pattern can be seen. Now, when you're thinking of the pattern, you're like, oh, I see this curved pattern. No, that's not like, it has to be very, very obvious. Like this one is obviously scattered throughout the whole thing. And this one is even less scattered, but it's still scattered throughout the whole thing. The one thing that you probably would want to say is that this is a very good fit in the beginning, but it tends to be a worse fit when you actually increase the x variable. I mean, that's probably what you would want to say. And as long as the appropriateness goes, that should be it for answer part B. For number 25. Okay, so 25, we have circled the unusual point. And obviously, can we all see that it's this one right there, far above the rest of the group? If this point was removed, describe the effect of the correlation. This obviously creates such a high residual with the line that your correlation coefficient actually went down. It's not a good fit because of this dot. If this point was removed, what I can visualize is that with these dots in the middle that's remaining, my line will tend to go more like steeper that way. Because this point is gone, it's going to tilt it towards in this direction like this, okay, the line. And so that it kind of goes through in the middle of all of those dots to minimize the residuals. So if this point was removed, first of all, if I were to comment on the least squares regression line, the slope will increase. Technically speaking, the slope is increasing in the negative direction, increase in negative value. And the y-intercept obviously you can see that it's going up. So the y-intercept will increase. If you actually say that the slope is going to decrease in a sense, because if the slope of this was -1, now you're going to -2, you can also say the slope will decrease. That will be the same thing as increasing in the negative direction. It means the same thing. So these two should be okay to do. Now for the correlation will obviously increase, because by removing this point, what you're saying is that the point that was high, residual, having the high residual is now gone, which means now all the dots are much more compact. The dots are closer to the line. The data points are closer to the line, or we can say residuals or standard deviation thereof has gotten smaller. So the residuals have gotten smaller, your standard deviation of the residuals has gotten smaller, so your R value has increased. So that's what you can say for part B. C, how would you classify this point? I would call this an outlier, which influences your slope and the y-intercept as well as the R value. Now, I know the answer key says that we need more data points to say it, but most likely, I mean, it is going to be influential no matter what. I mean, I can clearly tell that this has a high residuals here, and it's going to impact your R value, and it's going to impact your slope. So we're going to call it an outlier, also as an influential point. Okay, so down to I believe our last question for the day, which is a scatter plot that shows clearly an exponential pattern. This is the Moore's law for the transistors, doubling every 1.5 years, I believe, or doubling every 1.5 years. I think that's what they said. Yeah, 18 months. All right. So anyways, so going to this, it seems like we took the natural log, guys. Ln means log base E. Don't forget that. So we took the log of the transistors on the Y scale. We left the X alone. You can see that there's clearly a linear relationship between those two variables. State the equation of the least squares regression line. So it's a transform the data for this. So the way that you do it is natural log of Y hat is equal to the slope 0.36583x plus 7.0647. Don't jump in right away saying that the intercept or the equation of the LSRL will always start with y is equal to. We have encountered how we transform it. It can be having logs. It could be having natural logs. We have to be aware of that. Use your model to predict the number of transistors in 2020. 2020 means it's going to be actually 50 years from 1970. So for this, I'm actually going to plug in 50 into X. And then we're just going to simply just use the calculator. And we're just going to use that to predict it. So going to my calculator, I'm just going to type this all in. 0.36583 times 50 plus 7.0647. And then you get 25.3562. I think that's the answer also they have, which is ln of y hat is equal to 25 points. Let me just pull it up here again. Yeah, 35. So if you leave it like this on the day of the test, obviously I'm not going to be happy because the y variable is still not like by itself here. So you need to be able to take that and transform it into what we call an exponential format. So natural log of y is equal to this means that the base, which is e, raised to the output number, which is 25.35, will give you the input number, which is the y hat by itself. So to transform this into an exponential format, if you need the reference guide, this is transformed as a to the power of b to the power of a is equal to x. So I'm going to take e raised to the power 25.3562 is equal to y hat. So what that means is I'm going to actually go here. And where is e, you might ask? E is right here. Natural log, the left button of 4. It will give you e. And I'm going to type in 25.3562. Gives me, it's going to be a huge, huge number. Because in 2020, which is, obviously it's 2 years ago, but we have billions of transistors now in the computers nowadays. So I believe it was 1.11 times 10 to the, oh, I'm sorry, 1.028 times 10 to the 11th power. So, and if you guys don't know how to read the E value, the E just represents times 10 raised to that power. So you can see how it says 11 at the end. That means 10 to the power of 11. And that simply translates into that, if you can just remember that as well. So predicting we have these many transistors in the year 2020, which is a lot, as obviously you can see. All right, so I believe that should summarize the entirety of chapter 3. Hope this video helped, and I will see you guys on Tuesday for FRAPI, and also, I'm sorry, Monday for FRAPI and Tuesday for the test. Have a great weekend. I'll see you.